Hello! In this video, I will introduce and describe the new ADASH Advanced Balancing module. This module is available for VA5 Pro Analyzer and it will be also in VA3 Pro Analyzer. All of you know the standard balancing procedures. It is one plane balancing with one measurement point. It is two planes balancing with two measurement points. And generally speaking, it is all balancing jobs where the number of planes is equal to the number of measurement points. Now we should discuss a little about balancing procedures. If the rotor is unbalanced, then the heavy spot exists. The real balancing is the procedure when we find the position and weight of the heavy spot and then we remove it, or we mount the same mass to the opposite position. How we can find the heavy spot position and weight? There is, for example, an old method where we spin the rotor and we wait until it stops. The heavy spot position will settle on the bottom. How to calculate the weight of heavy spot? It is simple. I use the trial mass. Its weight I mark as Tm. I mount it, for example, 90 degrees from heavy spot position. I again spin the rotor. I wait until it stops. I am lucky when it stops in position when the distance of heavy spot position from the bottom is equal to the distance of trial mass position from the bottom. It means that the weight of heavy spot is equal to the trial mass weight. I must just move the trial mass to the opposite position of heavy spot. Now I use the smaller trial mass. I spin the rotor again and I wait. The distances are not equal, then I draw the vectors. The heavy spot position is deflected of the angle alpha. I draw the line with length equal 1. Now I draw the line in 90 degrees angle. It is the angle of trial mass against heavy spot position. I draw it up to the vertical line x. The length is 0.25. Now I calculate the k value, which is equal 1 divided 0.25. It is 4. It means that the heavy spot weight is 4 times higher than trial mass weight. Next method, how to find out the heavy spot weight, is based on time measurements. I begin on the position when the heavy spot is in the bottom. Now I deflect the heavy spot of 90 degrees. Now I release the rotor. It rotates forward and back. I measure the time of one movement forward and back. I mark the value as T1. Now I mount the trial mass to the rotor. I mount it to the heavy spot position. I again deflect the rotor of 90 degrees and I measure the time of one movement forward and back. The time value I mark as T2. The weight of a heavy spot I calculate from this formula. This procedure is absolutely correct. There is no side influences. I don't care about bearing condition, looseness or other influences. But In real world, we are not doing that. We use vibration measurement. We want to decrease vibrations on speed frequency. It is the accurate description what we are doing. No mention about heavy spot. It is hidden in background. I want to highlight this statement. Balancing approach is decreasing of vibrations, nothing more. If the rotor mounting would be infinitely rigid and be mounted on infinitely heavy mass, then we cannot balance, because no vibrations occur. But the old spin procedures would always work. Now we should clarify next thing. It is a very bad habit to say, I measure on plane 1. Please understand that planes and measurement points exist. We mount the trial mass on planes, and we measure on points. The group of planes is absolutely independent of group of points. We just measure the response functions between planes with trial masses and vibrations on points. The balancing when points are between planes is the same as balancing with all points on one side and all planes on other side. Many articles contain information about points sensitivity. For example, this point is sensitive for unbalance on plane 1 and not on plane 2. You can find many articles about overhang rotor balancing, which contain many of such speculations. The real situations are just an infinite of combinations of bearing houses' rigidity and their influences. Please accept this statement. The planes are marked by numbers 1, 2, 3, etc. The measurement points are marked by letters A, B, C, etc. The number of planes must be less or equal to number of points. It is logical and simple. You can answer why as the homework. Now we can finish the introduction and begin the discussion about ADAS advanced balancing. Let's begin with example. I want to balance the wide rotor. This is basic scheme. The rotor and two measurement points. Correctly, I should do two-plane balancing with 2 points. But I have an access to the plane 1 only. The plane 2 is, for example, under some cover and I have not access there. What to do now? I use the advanced balancing procedure. I need to enter two numbers in the beginning. The number of planes, it's 1. Next, it is the number of points, it is 2. Next steps are the same as for standard balancing. I use two sensors for point A and B. The first run is the initial run. I get the amplitude and phase for each point. Next is the trial run. Again, two measured values. Now the result is displayed. It is the final mass weight and angle. But what does it mean? If I have access to both planes, then I do two trial runs. Then I get the two masses for plane 1 and plane 2. The vibrations should decrease theoretically to 0 when I mount them. But if I can mount mass just to plane 1, then I get residual vibrations in both points. And this is the key point. I won't get the residual vibrations as low as possible. And this is actually what advanced balancing can do. Now, the deeper view to this example. I split the balancing to two jobs, each with just one plane and one point. Then I get two results, two balancing masses, mass A for point A and mass B for point B. I can draw them to complex plane. Here is the mass for point A and here is the mass for point B. I can imagine two cones with different steepness. For every point in complex plane, I can read residual vibrations in point A and B. It is clear that our required lowest solution must be on the line which is drawn between points mass A and mass B. But where? I can make the vertical cut plane through the both points. Now I draw just the look to this plane. I can see two V shapes. The optimum result for each point separately are the mass A and mass B points. Where are the residual amplitudes for that points? For mass A is the residual vibrations equal 0 in point A, and here is the residual vibrational amplitude measured in point B. For mass B, I get the 0 in point B, and here is the residual amplitude in point A. I need the compromise, and it is here. In this position, I get the lowest residual amplitudes in both points. Now we return back to three-dimension view. We can simply evaluate the required balancing mass and angle for plane 1. When we mount it, we should get 7 mm per second amplitudes for both measurement points. If we have n planes, then we would work in n planes dimension, and to imagine it is not so simple. This example was the simplest example. You can define up to 8 planes and up to 8 points. For example, 1 plane and 4 points, or 1 plane and 8 points, or 4 planes and 8 points, etc. The basic reason remains usually the same. I don't have access to all required planes. Of course, you can enter the equal numbers for planes and points. Then it is standard balancing procedure, for example 8 planes and 8 points. The advanced balancing gives two solutions. It means two sets of final balancing masses. The first is made by L2 norm. By other words, it is the least squares method. It means that the sum of residual squares is the lowest possible value. The second result is made by L infinity norm. The maximum of residual vibration is the lowest possible value here. Are you confused? Don't worry. Let's show the example. If I have 1 plane and 4 points, then I have 4 residual vibrational values. Now I will overact 2 results which I get. The L2 results is 5, 0, 0, 0. The L infinity result is 3, 2, 2, 2. Now it is on me what result I prefer. The possible result is also no result. It means that adding of any masses in any positions will increase the vibrations. But in real life, you probably will not get this result. but with special theoretical values it is possible. For example, I have one plane and 2 points. The init run values are 10 mm per second amplitude and 0 degrees angle for both points. The trial run values are 14 mm per second and 45 degrees in point A and 14 mm per second and 315 degrees in point B. In this situation, no mass will help you. Try to find out what is the reason. If you want to decrease amplitude in point A, you must turn the mass off plus 90 degrees. Then you get zero vibration on point A, but 2 times higher vibration in point B. When you turn off minus 90 degrees, then you decrease vibration on point B, but you increase vibration in point A. The advanced balancing gives also the sensitivity information of results. What is it? It means what would be the residual values when I mount the masses with some error in position and weight. I use the example again. I have one plane and 2 points. The result is 100 grams mass weight and 90 degrees angle position. The residual amplitudes are 2 and 3. But I mount the mass with some error in weight and angle. The percentage residual values informs me what would be the residual amplitudes if I mount the mass with 5%, 10% and 20% error. For example, I get 2.1 and 3.2 amplitudes for 5%, 2.2 and 3.3 amplitudes for 10%, and 2.3 and 3.4 for 20% error. This is low sensitivity. I can mount the mass with error and residual amplitudes does not increase too much. But I can get 5 and 6 amplitudes for 5% error, 10 and 12 amplitudes for 10% error, and 20 and 25 amplitudes for 20% error. It is high sensitivity. I must use accurate weight and accurate angle to achieve the low amplitudes near 2 and 3. In the end, I answer your homework question. It was, why the number of planes must be less or equal to the number of points? The answer is, if the number of planes is larger than number of points, then I can use just many planes as the number of points is. And then it is standard balancing, where both numbers are equal. I hope that Adash Advanced Balancing will help you in many practice situations. Thanks for watching.